So good evening everyone. Welcome to the week 10 of Fundamentals of Additive Manufacturing Technology. Okay, so today we will discuss on powder feed based additive manufacturing method. I hope it's audible to all of you. It's audible, right?
Yes,
Yeah,
yes.
okay. Thank you. So as you can see, there are two types of feeding system, off axis and coaxial feeding system. Okay, so So today we will discuss on some questions, numericals and some theory-based questions. So these are the two types of mechanism that can feed the powder particles in the laser beam. Okay, you can see the laser beam here and here. Okay, so okay, so in this type of additive manufacturing process, we don't use electron beam. We do not use electron beam. Because in electron beam type of additive manufacturing process we need a vacuum, and here we are mixing the powder particles in the inert gas or shielding gas like argon or nitrogen. Okay, so if you are using a gas, that gas cannot create a vacuum, so it is not possible to use the electron beam in powder feed based additive manufacturing process. I hope it is clear. So I'll just write why we can't use we are using inert gas, so it's not possible to create vacuum. Okay, so in this as you can see, we have two different methods by which we can feed the powder particles: off axis feeding system and coaxial feeding system. So here we this we have a separate, it is not a coaxially aligned with laser beam, we have a separate feeding system, which as you can see. So in this feeding system, powder plus gas is coming. So function of gas is to prevent oxidation. Okay, fine. And this gas carries the powder particles. By changing the pressure of the gas, we can change the concentration of the powder particles. The, now this is about off-axis feeding system. Now in coaxial feeding system, we can see the laser beam is coming from the center, and from the periphery we can see the powder particles are coming. This is the powder. Okay, so these are the powder particles are coming. So it is like this, the laser particle, and this is the powder. So it is easy to control the stability of the control the stability of the molten food. Why it is so? Because here we are feeding the powder particle coaxial, but here we have to maintain at an angle. If my angle or speed is not optimized, then we cannot do the feeding system. Okay, carry out the feeding system. So it is very easy to control the molten pool, stability of the molten pool. This is the main difference. Now in off-axis feeding system, we have to put it in a the quality of the. It is not difficult to control the quality of the feed. So as you know, this is the application of this type of process. It is also in one of the assignment questions. So in this we have a substrate we are depositing our feed. So this process can be used for laser cladding. So what is laser cladding? This is a workpiece and this is a gear. I have a teeth. So the hardness of the teeth should be high. Should be high to reduce wear. So instead of making the whole gear as a wear resistant material, we can just make the teeth as the wear resistant material. Okay, improve the hardness of the teeth. This can be done by laser cladding. Hardness of tooth, hardness of teeth. So this can be done by laser cladding. So there is a layer and we can put a different material on the base substrate. Plate with a titanium. Titanium, this is mild steel. So the quality of the product will be improved. This is laser cladding. Okay. Now part restoration. Part restoration. Turbine blade. Now this is turbine blade. Suppose consider it is broken from this side. Now from this portion it is broken. Okay. This is broken. Now there is either you have to replace the whole turbine or okay. So in this case what we need to do is we have to find out how to rectify it. If we want to just restore it, then we can use we we can deposit the material in this portion and this component will be restored. So this is a part restoration application. And next one is such application is like when we are doing our old monuments, we are using such type of application. Part restoration. Okay. Ancient monument repair. So this technology is also used. Okay. Next is surface alloying. Surface alloying is similar to laser cladding, but in laser cladding we can see that the base substrate and the deposited material are different. At the interface, this interface is visible. Okay, it is possible to differentiate between the interface and the substrate, but in surface alloying we cannot differentiate. Suppose we can melt the top surface and we can put some particles. This is your base substrate. Let's take it as mild steel, and we want to increase the wear properties or hardness of the surface. Okay, we can melt this much layer, melt and put powder particles. So at high temperature, they will react with the atoms and molecules of the base material and form a compound, and this compound they will form a alloy. So this is a surface alloying. So in laser cladding, it is possible to differentiate the difference between substrate and the surface because of this interface, but in surface alloying, it is not possible. So this is, I think, the assignment question. Okay. So one part we covered. Next is Now, in off-axis feeding system, we'll discuss something about off-axis feeding system. Okay, I'll go on to next slide. Okay, this is about off-axis feeding system. Mm, yes, yes, yeah. Because we are see here, we are putting melting and putting the powder particles, so a compound is formed. So this interface is not visible. Okay, but here we are not melting it. We are just putting it as it is. Mm-hmm. Yes, yes, we are using the powder bed only. We are using the powder bed. Yes, 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 we can use the powder bed method. Are different. Laser cladding and surface alloying are different. Only small differences. This interface is visible in laser cladding, but it's not visible in surface alloying. But both the methods we are using in powder bed. Yes, because see here we are melting and putting the powder particles. So an alloy is formed. Okay, so since an alloy is formed, that there is a temperature. Exactly, we cannot say temperature different. That again depends on the material and what substrate and what particles you are putting. But there will be an difference in since a compound will be formed. Okay, so alloy is formed. Since an alloy is formed, so obviously the properties will change. So in that way, the difference is there. But here the individual that will be differentiated. Yes, yes. Yeah, yeah. Okay, okay, where is it? So in off-axis feeding system, will now this is the laser beam. Okay, the angle between is theta. The powder plus gas is feeded. Now top surface is this is the top surface. Okay, and this white and black color, this is the which is in the form of ellipses. This is the projected area. This projected area. Okay. Now, some questions are related to the catchment efficiency. What is the catchment efficiency? We'll discuss. Okay. So it is the ratio of mass of deposited layer by mass of powder ejected from the nail nozzle. So suppose this is mass of okay. This is the bead. The mass is this. Now the powder what I am supplying is more as compared to the deposited. So some of the powder will not be deposited. So some of the powder will not be deposited at the given temperature. Okay, I think someone needs to mute. So some powder particles which are not deposited, they remain outside of the bead. So the mass of the project powder ejected from the nozzle, this will be MA. Okay. So efficiency is equal to MB divided by MA. Okay. So this is what your mass of deposited layer and mass of powder ejected from the nozzle. the nozzle. Okay. Now I'll just write what is that. Absorbed power is P naught, K thermal conductivity, T naught is room temperature, Tm is melting point, and dP is diameter of projected area. Okay, now I'll go to a question from your assignment. I have changed some values. Half I have changed. Okay, so this is the question. Powder feed based additive manufacturing process and off-axis nozzle is used to feed material into the molten pool. So if the material is changed from A to B and same setup is used with same process. So suppose material is changed from mild steel, just example I am giving, mild steel to titanium. Okay, setup is same. All the process parameters, input parameters are same. Melting point of material A and B are also same, but the thermal conductivity of material B is half times slower than the thermal conductivity of material A. Find out the ratio of the catchment efficiencies for both the materials. Okay, so here now MA is equal to K, MB is equal to K by 2. Now the formula which we now just discussed, P square cos theta by dP square K square Tm minus T naught whole square. So theta is this theta, angle between the laser beam and powder. Now this theta you know. Okay, now dP, as you know, here I have just mentioned diameter of projected area, and K is the thermal conductivity, and this P naught is the absorbed power. So you okay, so now you are aware of all what are each parameters. So we can see nothing is given. Power is not given, theta is not given, dP is not given, temperature is not given, only K is mentioned. Okay, what we have is K. Now efficiency is inversely proportional to square of thermal conductivity. So if I have to take the ratio, so I have to find out related to this. Okay, thermal conductivity. So efficiency of A divided by efficiency of B, this will be KB by yes, K square. Okay, you put the values and K by 2 square divided by K square, which will be 0.25. The answer is 0.25. Okay, so we'll now go to the next question. So, you feed. So you have a powder feed based additive manufacturing. Off nozzle is used to feed material into the molten pool. Now the off axis nozzle is mentioned. If the power of the laser is increased by that 4, then the catchment efficiency will increase by how much? Okay, now we'll again go to the. Please mute yourself. Yes, I'm just writing. Now efficiency is proportional to power square. Okay. So if the power is increased by 4 times, then efficiency will be increased by 4 times 16 times. Okay. Okay. 16 times. Some. Now, to calculate how the particles are distributed in a unit circle, so it is in a Gaussian distribution. Okay, laser distribution also we are taking Gaussian. It is not perfectly Gaussian, but to simplify the calculation, we are taking it as a Gaussian. So we are considering it as a Gaussian distribution so that because it is comparable. Okay. So based on this, now if you take a Gaussian distribution, you can see that in coaxial delivery system at any point the x is y axis. Okay. I'm taking this point. Okay. Distance of this point from center r. Let's make it small. So this point of coordinates are x comma I. Okay. Number of particles at x comma y. Okay, just a second. Is it okay now? Yeah. Huh. So, so this in the coaxial delivery. So, okay, this where's the to find the number of particles here? N A x comma y is equal to n naught exponential of minus r square by n naught is the weak particle concentration, peak number of particle concentration. Now peak is at the center. Okay, this is the center. And r, you know that is the length, and k is the constant. Okay. Fine. So at center. Fine. Now we have to calculate the value of n naught. Okay. So we have to this is somewhat, I think, some question it is there. So how to calculate it? So if I take it, suppose we consider at the periphery. This is the periphery. Okay. Now at r is equal to r, n a is equal to n naught by e square. Now we will compare these two equations. This equation 2. So this will become n naught by e square is equal to n naught exponential r square by k square. Now after solving this equation, our K will come, K is equal to 2 by R square. Now you have got the value of K. This K value you will put it here. Okay. For N naught, we will take this whole thing. I'll draw it here. For whole strip, I'll take a area for a strip. How many particles will be there in this strip? Will integrate it. Okay. So that will be NP is equal to 0 to infinity. Since we are taking this to infinity, okay. N naught exponential minus 2r square by r 2 pi, this area will be 2 pi r dr. So this, on solving all this, you will get n naught is equal to np divided by pi r square. Now this n naught value put in this equation. See, this you put it here. Okay. So NaXy, this will be 2np by pi r square exponential minus r by k square. Fine. Now one question is from the projected area. It is interrelation between the cross-section area and the projected area. Projected area is A by cos theta. In some question it is given it as 30. Okay. So how you will calculate it? How to calculate this area? A will be normal pi by 4 d square. Okay. So theta is given, d is given, you will get pi by 4 d square by cos theta, you will get the projected area. In some questions it is also given, asked for this. Okay, where were we? We were discussing R. So this we did discuss, we found out N naught and we found out the number of particles. Okay, now we will discuss next question. Now we'll discuss coaxial laser system. Now in off-axis nozzle system, we discuss the catchment efficiency. So here also we have a efficiency which is known as the primary efficiency. So here also the initial formula is same, depositing by supplying, amount of by supplying. But whatever the final we get is different. This is also somewhat quantity of deposited powder total powder supply. NP is equal to 1 minus exponential minus W square divided by 2R Z square. Okay. With W width, R is the radius. Okay, this is Z square. Width is given in some question, R is the given, and you will get all the values, you will get the primary efficiency. Now we will go to the next slide. So now we have to find out where we have to use such nozzle. Okay. The question is, where will we use such nozzle? Okay. So in the powder bed system or wire gauge system, we cannot make a support structures. Okay. Support structures are not allowed. So if print a print a support structure after printing, it is very tedious to remove it. So so in those cases we can use a 5-axis or 6-axis system so that we have overhanging fixture. This is the component which I am making. Now this is your base plate. Okay. This is your base plate. Now till this problem there is no problem. Now at this point here there is no support structure. We are printing it like this. Okay. So what will happen? This will be overhanging. Now so here there is no powder bed. Okay, this whole thing, this part is hanging in the air. Okay, so to print it easily we can rotate it easily. Okay, now our component will be like this. Just rotate it. Now this is possible to deposit here. So when we get this point, we can again rotate it and deposit the remaining portion. But if we are rotating and our nozzle size is like this, what is the problem? There is a possibility that nozzle try to strike the normally already deposited deposit. Okay, so that is why in this case we are using such type of nozzle. Now non-planar FD. So this is the XY, the multiple nozzle. Okay, this is an FDM. Now plate will provide the Z-axis motion or nozzle will provide the Z-axis. Now nozzle will always be perpendicular. It will always be perpendicular. It will like this. It will never be like this. Now if it is perpendicular, it is planar FDM. Okay. So nowadays we can rotate it. We can rotate the nozzle. But if your nozzle size is less, so at this point it will try, when it is very small, less, it will try to hit the already deposited layer. Okay. So now you can rotate. So this nozzle is very much beneficial in our earlier discussed application, laser cladding surface alloying. Okay, we can make some grooves. Now Now, if you, as I already said, if the nozzle side is very less, it will try to strike for the already deposited part. So if we have a long nozzle, it will be easier to manipulate and control the motion of the nozzle. So this is the places where we can use such type of nozzle. So for a particular application only we are using such type of nozzles. Otherwise we won't use because it will be very difficult to control the function of these nozzles because all the thermodynamics that is used in 3D printing process it will be different for this type of nozzle. But we okay we cannot in it's yes, yeah, yes, yes. So, like we discussed just now, the Gaussian distribution, all those things we cannot calculate. We cannot calculate to thermodynamics, heat transfer, everything will be changed in such type of nozzle. Okay, and yes, yes, see, okay. So, fine, next we will move on to functionally graded materials. Okay. So, functionally graded materials will be like as you are seeing. Okay, suppose I'll just explain first what is it. Suppose this is your specimen. So here there will be various types of functionally grading. Okay, like your density will keep on increasing from top to bottom to top, or it will go on decreasing from uh, top to bottom. Sometimes your material will change from top to bottom, or this material will density material. Your structures may vary from top to bottom. So with the increase or decrease in layer your material properties or your density or your color may change. Okay, so fine, this has this too but density based or material based has more effects on mechanical process. Mechanical and thermal, in short we can write physical process. So for the density base, we can see this like example, cross section of bamboo tree, palm stem, dinosaur bone. This is density. Just a second, please. This is the density based. Okay. This is the cross section of bamboo tree, palm stem, dinosaur bone. Now, this is a human bone, which you can see. So here you can see the pore size is much higher as compared to the other periphery. Okay. Now here the pores are bigger and here again small pores are there here at this region. Here also you can see pore size is vary. Okay. So you can see with change you can have more porosity as I was saying here. density valve vary. So here that is what happening. That is functional grading. So it will be complete. Some parts are complete solid. Some are 90% porous, 80% porous. Some are 70% porous. Okay, so this has high stiffness to width ratio. Now, why we are doing it porous? When the weight of the complete body is solid, then that weight will be high. So, for this reason, we make it functionally graded. Okay. So, and why another reason of making it functionally graded is in our body, like you can see, this is an example of a teeth. Okay, human bone. So, so we have some fluid in our body which depends on the porosity. So it will be easier for the fluid to flow inside the bone if the porosity is higher. Okay. So this type of functionality is dependent on our porosity. Now next thing is our modulus. If you see our bones has a modulus of uh, around 20 gigapascal. Okay. Calcium sulfate. So these have high density as compared to 20 gigapascal. Okay. So how this modulus decreases? So this modulus is decided by our functionally gradation. Okay. Here also we have this in steel. You will see the porosity changes from here to here. Copper also porosity changes. So this is taken from a paper. Okay. So these were some live examples where I wanted to show how in real life also functional gradation occurs. Now this has been incorporated in our uh, scientific work also, where we have used various functionally graded materials by biomimicking those properties in our real engineering applications, where we are biomimicking this structure of bone or butterfly wings or uh, some sphere in exoskeleton, and these are some basic examples, or pigeon feathers, some examples where we are taking those structures and trying to print it. These computer structures we are trying to print in form of by using our various powder feed mechanism or different materials. So this was just an example for your functionally graded material. Okay, so now the next question. Okay, so these are some of the theory questions related to your just we discussed whatever. So first is, what are the following of the advantages of discrete coaxial nozzles in powder feed based mechanism? So now we already discussed continuous coaxial, discrete coaxial nozzles. Now in continuous coaxial nozzles, the head tilt can be accommodated, but in the head tilt can be accommodated in discrete coaxial nozzle, which is not possible in continuous coaxial nozzle. When this is suppose your so in continuous coaxial nozzle, The head tilt is not possible. And we also know that in continuous coaxial nozzle it is omnidirectionality, it is non-omnidirectional. But in your discrete coaxial nozzle, the head tilt is possible and it is uh, omnidirectionality can be achieved. So the correct option is both. Ability to manipulate carrier glass flow rates and pore velocities for individual powder stream, and omnidirectionality beyond 45 degree can be easily restored by simply increasing the drag velocity of uh, carrier gas, but this is not possible in continuous coaxial nozzle. Next question. Okay, which of the following are correct for efficiencies of nozzle in powder delivery system? Now, coaxial efficiency can be as less as 30%. Okay, central feed nozzles, this efficiency is above 80%. And advantages of central feed nozzle, that is the advantage of using central feed delivery nozzle. It has minimum divergence of the powder stream. So, according to this, efficiency of central feed nozzle is greater than the coaxial nozzles. Minimal divergence of the powder stream. Efficiency is above 80%. And coaxial efficiency as low as 30%. So efficiency of central feed nozzle is greater than um, coaxial nozzle, and this is the advantage also. Next question. Why are, yes, okay, why do we use coaxial? So you are saying that as compared to cheap cent hmm. Yeah, see here as we discussed, here it is easier. Only reason is it is easier to control the stability of the molten pool. Okay, where we do not create since it is easy to control it, so that is why we use it. The coaxial feeding system is mostly used. Mm-hmm. It, yes. Mm-hmm. Yeah, but about whether it is cheap or not, we cannot say it. I just don't. Yeah. No, no, no. That's not the reason. Functionality, owing to the functionality, it may differ. Yes. Yeah. Yeah. Yes. Yes, yes, yes. This nozzle and system, a lot of time, whatever it is inbuilt in the printer, okay, we can actually manipulate and change as per our requirement till it works. Okay, so we can always vary. So these are some of the basic systems which are given, but suppose you want to vary or change, it's always we can always do, so that can be done. So okay, This was in coaxial. And next question. So, why are gas powder delivery nozzles used with electron beam as a heat source? Okay, this we discussed, but I'll say it, that electron beams, as we discussed, this requires, here we discussed, okay, yes. So here we discussed about electron beams. In powder feed based additive manufacturing, we do not use electron beam because for electron beam we require vacuum setup and everything. So that is why are question is why are gas free powder delivery nozzles to be used with electron beam as a heat source? So use of electron beam, it requires very high mass flow rate, closed loop feedback control. Okay, now high mass flow rate, this leads to surface roughness and crack porosity. And when we have a this is the correct option. The use of electron beam requires a vacuum environment where carrier gases cannot be used for powder feedstock handling. Regarding this all, whether it requires a closed feedback control, high flow rate is obtained to prevent melt pool oxidation. Now, melt pool oxidation is prevented by shielding gas. So, additional provision of shield gas is provided for protection of laser optics from powder particles and metal fumes. And higher mass flow rate, I already said, it is related with surface roughness and crack porosity. And closed loop feedback control, fabrication of like it is used in powder delivery nozzles where multiple inputs are provided which can adjust its speed parameter with the delivery system. So these all are not related with your heat source. So correct option is option. Now okay. I wanted to say one more question. I just missed it. Yeah. What happens when the dilution ratio alpha is greater than 30% in laser cladding? Okay. Now alpha is equal to delta by beta plus delta into V. Now this is the optimal range for dilation ratio is between the first layer and substrate is 10 to 30%. Okay, so when alpha is greater than 30%, keyhole defects occurs, and alpha is less than 30%, your lack of fusion occurs. Now suppose this is your deposited bead, okay, and this is your substrate. This is your substrate. Now deposited bead, this is your substrate. So this will be, suppose if we take from here to here, just example, this will be beta, this will be delta. Now your total alpha is delta by beta plus delta into 100. And so when your dilution ratio is greater than 30% in laser cladding, as we mentioned, keyhole defect occurs. And the optimal range is this one. Now next one, the pneumatic feedstock powder handling system in the powder feed based additive manufacturing has which of the following features? Now uh, there are This is a very theoretical question. The pneumatic powder delivery nozzles, they have like sample cross section, total porosity, surface roughness. Some values are given in your assignment. Okay, so related with that, we have this the correct. I'll write the values. Pneumatic powder delivery nozzle. This is non-pneumatic powder delivery nozzle. Okay, so the sample cross section for this nozzles is around 8.6 mm square. Here this is 8.09 mm square. Total porosity for this is 0.015 mm square. For this will be 0.04 mm square. Surface roughness for this will be 2.14 micrometer. This will be 14.25 micrometer. Surface roughness. Okay, so this is according to a data by researcher Wang et al. Published in 2011. Now, according to this, um, the basic features for this powder handling system are that they are unable, they do not fabricate or they cannot make functionally graded material. They cannot uh, entrap inert gas leading to porosity, and sorry, they can entrap inert gas leading to porosity, and the surface finish is poor due to the deposited track due to high particle velocity. Okay, so these are the correct options. Now, there is no convective melting of the melt pool due to use of inert gases. So these are some things which we have to remember for this type of uh, feedstock powder handling system. Now, next, vibration assisted powder delivery nozzles is which of the following functions? Now, this is pretty simple. Uh, Vibration nozzles, vibration system, they use mechanical vibrations are done to transport granular material. Okay. Now, mechanical vibrations are done. So, according to this, acoustic vibrations can be used, ultrasonic vibrations can be used, and a water bath can be used for the uniform application of vibration to the powder delivery through a sonotrode. Now, this is carrier gases are not used. Here only vibration are used. This is the odd one out. Okay. Now here we use mechanical vibrations are done to transport granular material. Now next question. Which of the following is an application of powder based we already discussed laser cladding is an application, functional graded materials also we can do, part restoring machine. In short, the correct option is all. Laser cladding, which we know, similar and dissimilar material can be melted in order to obtain a new surface with the desired properties. Part restoration is uh, where we just where we discuss about a turbine blade, where this only part can be restored. How to actually how it is done? We talked, but I'll say it again. We change it to a mesh representation. This CAD input is provided, then it is analyzed for extracting the repair volume, and this toolpath planning is done. Okay, so this was all about today's question. Anything more we can discuss? Yes. Okay, so are there any more further questions? I I hope maximum of your questions and some related to your assignments have been talked about. I have discussed most things. Okay. If there are no more questions, we'll end the session. Thank you all for attending the session. Let's meet again next week. Yeah.